and say that phi is the distance in Y. So Y is initially a metric space. Distance in Y between, well, I forget to say, I want to define the metric, so I need to consider 2 points, R1, Y1 and R2, Y2, and I would like to write down what is the distance between them. So first I consider such an angle. And then I just take on standard Euclidean plane 2 points which are on this angle phi, one from each, two rays with angle phi. I take here a segment R1, I take here the segment R2, and this will be the desired distance. So if I have 2 such points, then I would like to say that distance, this is the definition of distance in x. Distance in x between x1 and x2 is as follows. Well, we know very well how to compute this length. It's just the cosine law. So it is square root of r1 squared plus r2 squared minus 2 r1 r2 cosine of phi. Okay, that's the definition. But this definition works not everywhere. Well, this definition works only if this angle phi is actually an angle. It is, of course, we can write down this in arbitrary situation, but this is senseless. The idea is that, okay, if 2 directions in y, so here is y, and we construct metric on such cone over it. If 2 directions are very far from each other, say this distance is equal to 1000, then this cosine depends only on the integral part of this to 1000 modulo 2 pi, and this is a very stupid way to introduce such metric. So the idea is that if they are very far from each other, the metric shouldn't oscillate. So the idea is, look for a moment. This is definitely good formula if phi doesn't exceed pi. Then it's okay. But if phi does exceed pi, then we need to introduce something different. But look, what happens if phi equals to pi? If phi equals to pi, then our distance, then that formula gives us just r1 plus r2. Well, so if such angle is pi, then distance is r1 plus r2. What does it mean? This means actually that the shortest path between these 2 points are through the apex of the cone. This is exactly r1 plus r2. And it is natural to introduce such a metric that when the angle is larger than pi, then the shortest path is still through the apex of a cone. So the correct definition is like that. And in the case phi equal to pi, both formula gives the same. Well, so this is just a formula. We take this space and introduce the metric in the following way. Obviously, if we take for y the sphere of radius 1, then we obtain usual flat matrix, Euclidean matrix in Rn. What will happen if we take let us consider even simpler situation. If y is circle, if y is circle of length 2 pi, circle of radius 1 is circle of length 2 pi, then we get flat metric of flat metric of usual Euclidean plane. But what happens if we take circle of smaller radius, so of smaller length? Then we just take usual cone, which can be embedded in Euclidean 3 space, such usual cone it is still locally Euclidean, but it has some angle defect at this point. The total angle around this point is not 2 pi. And similarly, we can consider such a cone when the length of circle is greater than 2 pi. Then, then it cannot be embedded isometrically to R3, but still we can define this. And this is exactly this construction. So when two directions are on the angle smaller than pi, then it is shorter to go directly by such line than to go through apex. If the length becomes larger than 2 pi, then it is shorter to go through the apex. Okay, so this is definition. This definition was known at least to Alexandrov and maybe even earlier. This is very old construction. Well, but what can we say? We can say immediately that, so first lemma which we need to check, of course, is that if Y is a complete geodesic space, then what we obtain is is also a complete geodesic space. So if Y is complete geodesic space, then such X is also a complete geodesic space. Well, actually, of course, we need to start with checking that this X is a well-defined metric space. A priori, we could we need to check the triangle inequality. Yes. So yes. I would like to say it explicitly that of course we have a special point, which is this apex point when r is equal to 0 and phi is undefined. And of course, its distance to any point y is r. So this is distance between 2 points of such type. Okay. So first of all, why? Let us maybe I will not be very precise here. I just would like to explain that this lemma is almost obvious. Well, first, let us understand what can we say about triangle inequality? Here in all statements we have some enumeration of cases. Since we have two cases here, if we have 3 points x, y, and z, and we would like to check the triangle inequality, let them be x1, x2, and x3. R1, y1, R2, y2, and R3, y3. Then, okay, there are, well, several cases. For each pair, we can be either in this case or in this case, so we have several cases. Also, we should keep in mind that one of the points can be the apex, and this also adds some cases. Actually, all this enumeration will today occur several times, and it will be very boring if I just make it very explicitly. So I will usually the most interesting, the most conceptual case is when we are always in this situation. And all other cases are usually very easy, and I will usually skip them just to save time. So, well, if we are in this situation all 3 times, then what can we see? Okay, so if we consider these 2 points, y1, 3 points, y1, y2, and y3 are 3 points in y capital. So we are in the case when distances between them are all less than pi. And of course, since y is a well-defined metric space, we know that these distances satisfy triangle inequality. Yes? So we have these 3, well, let phi ij will be the distance in y between yi and yj. And those 3 distances do satisfy the triangle inequality. What can we say? And all of them are less than or equal to pi. Yeah, this is our case. What can we say? It would be nice to find a triangle, a spherical triangle with those 3 lengths. Suppose, assume for a moment that such triangle exists. So assume that we have a usual 2 sphere of radius 1, standard sphere, and on this sphere we see a spherical triangle with those 3 side lengths. Then we can consider such rays from, this is the center of the sphere, such 3 rays in Euclidean 3 space. We stand in the standard way, we embed S2 into R3, and then we get, so this is point 1, this is point y1, this is y2, and this is y3, and on each of these rays we take segments of lengths r1, r2, and r3 respectively, and now we see that our distances given by this formula are exactly these Euclidean distances between these 3 points, and of course they do satisfy the triangle inequality. So this case is rather clear. But okay, when such a triangle exists, such a triangle exists only if the sum of these 3 side lengths, so if we would like that there exists a triangle on the standard to sphere with given side lengths, then there are two necessary and sufficient conditions. First, we need to have triangle inequality, and second, we need to have that the sum of these side lengths is less than or equal to the equator of the sphere, which means less than or equal to 2 pi. So this is not necessarily true. We have 3 angles, which of them is not greater than pi, so their sum can be greater than 2 pi. If it is not greater than 2 pi, then okay, that's true. But if it is greater than 2 pi, we need also to care of this case. Well, if it is greater than 2 pi, then actually the situation like that is like that. Actually, it is not hard to see that any of these distances is monotonically increasing when phi increases. So this is a monotonic function in phi. Well, this means the following: that if we want to check triangle inequality, say this one, x1, x3 plus x2, x3. Well, all these 3 guys are certain functions in these functions in R i's and phi i's. Well, if we decrease phi to 3, then this term also decreases and all other are constant. Since each angle is less than or equal to pi, when we decrease phi to 3, then we first, this inequality will happen before phi to 3 becomes 0. It is earlier. So we are in this area, and we start decreasing phi to 3. But we know that the sum of those two is smaller than 2 pi. So we start decreasing it, and we achieve this inequality before phi to 3 becomes senseless. Phi to 3 cannot be smaller than 0. This is senseless. But we decrease up to some, actually up to this, which is 2 pi minus phi 1, 2 minus phi 1, 3. We just can replace phi to 3 by, there is no need to consider such process. We just can replace it by a smaller angle. And it is still greater than or equal to 0. And we see that if we take phi to 3 prime, then this term becomes smaller, but the inequality is true. So it is true from the very beginning as well. Well, so there are such rather not so hard similar arguments in the case when some of those phi's are greater than pi. So I just don't want to consider all these cases. So, okay, what we see? We see that this X is a well-defined metric space. Now, why it is a well-defined geodesic space? It is a well-defined geodesic space since we can point out geodesics explicitly. In the second case, it is very easy. There is a geodesic which comes from the apex. Okay, this is if this phi is greater than pi, greater than or equal to pi, then, well, here is an isometric embedding of the segment. We just go through this apex 0 from R1, Y1 to R2, Y2, and this is geodesic segment of length R1 plus R2. But, okay, in the case of but in the case when R1, I prefer to write down it here. What happens in the case when we would like to consider geodesic between such 2 points? When this is less than or equal to pi. So suppose that distance in y between y1 and y2 is less than or even strictly less than pi, the case equal to pi also covered by that. Then the geodesic is like that. We need to take the geodesic between y1 and y2 in y capital. So let this gamma be a geodesic between y1 and y2 in y capital. Then we have such cone over this geodesic. And points of this geodesic are naturally parameterized. If this is phi, then points are naturally parameterized by this angle parameter, which goes from 0 to phi. This is just naive, how it is called, natural parameterization by length. And to describe, so the geodesic will lie here, and it will go, it will be given in polar coordinates by certain function. Oh, well, let this be phi 0, and phi will be a current coordinate. So here we need to have such function. Well, and this will be exactly those functions. If we consider, I don't want to write down explicitly, but any of you can do it if you want. If you consider a triangle, a Euclidean triangle with side lengths R1, R2, and angle phi 0 here, then for any angle phi, you have this length R of phi. So this is standard trigonometric how the Euclidean geodesics can be written in polar coordinates. I don't want to write down trigonometric formulae, but it is completely straightforward. Well, and again, we see immediately from this definition, that this is actually a geodesic. This is actually a geodesic since, okay, for any 2 points here, we see that distance between them is computed exactly as distance between the corresponding 2 points here. So here is actually this is isometric embedding of the whole triangle. We can feel this triangle, and this is isometric embedding of it. Just because the distance is computed by such standard formula. Well, an important, I have described how geodesics looks like. Note that, of course, geodesic can be not unique. The matter is that a geodesic between y1 and y2 is by no means unique. So we can take any geodesic between y1 and y2, and we will obtain geodesics between the corresponding points. But an important, though simple, observation is that what I have described is exactly all geodesics. There are no other geodesics except for those that I described in this way. The matter is that this function, when we are in this region, this function is strictly monotonic in phi. So if instead of a geodesic here, we take a somewhat longer curve, then we necessarily get a longer distance between these points. And also, if we so if vice versa, if we take any geodesic from x1 to x2 in x, then we can project it radially to y. And if we get not a geodesic, then the initial one was also not a geodesic. And if we get a geodesic, but we use another function r of phi, then again, this will be longer. The only way to obtain the shortest possible path is that we take a geodesic gamma here, and we choose exactly this function r of phi. So all geodesics looks like that. This will be important for us. This is not important for this lemma, but this will be important. We will soon try to prove lemma 2 about how cut kappa properties are related for y and x. Well, there is also this complete, but let us more or less skip this as an exercise. It is not, well, roughly speaking, if you have a fundamental sequence of points in this metric cone, then this yn is necessarily a fundamental sequence in y. And Rn is a fundamental sequence in R+. Both of them have limits, and this is exactly our limit. So this is more or less straightforward. Okay, we have this construction, and the most important in this construction is the following lemma. We would like to obtain some connection between metric properties, curvature properties for x and for y. Well, what we know? We know that if y is a sphere, a round sphere of radius 1, then x is flat, is Euclidean. We have property which, if we compare something with a sphere, this is cut1 property. If we compare something with Euclidean space, this is cut0 property. So it is not so surprising that the claim is as follows. X is this metric cone over y with that metric that I described. X is cut0, if and only if y is cut 1. So this is a very nice criterion. Let us understand how to prove this. Again, we have several cases. We have what should we consider to prove this theorem? We need to consider any geodesic triangle in X, and cut zero property is that any geodesic triangle, if we construct a comparison triangle in R2, then then the initial triangle is thinner than this comparison triangle. Cut 1 is the same for with sphere instead of Euclidean space. So we need to construct a comparison triangle on sphere of radius 1, and we say that the initial triangle is thinner than triangle, the comparison triangle in the sphere. So again, when we consider, when we start considering a geodesic triangle in X, we again have several cases. For any, we have two kinds of geodesic segments. One of them is like that, when the distance in y is less than pi. And the second one is geodesic segment through the apex when the distance in y is greater than pi. So we again have several cases. I would like again to consider only the first of them. And for others, there is some enumeration which is not hard. Okay, so assume that assume that what I would like to assume? I would like to assume that if we introduce these distances in y between yi and yj, they are all smaller than pi. Let us consider only this case. In fact, we need to consider all other cases, but it is not so hard. Okay, let us consider this one. Again, we have two subcases. It can happen that the sum of those three angles is less than or equal to 2 pi. And then there exists a comparison triangle into sphere. When we check cut 1, I recall that when we just in the definition of cut 1 space, the definition was that any triangle must be thinner than its comparison triangle whenever comparison triangle exists. The matter is that if the perimeter is greater than 2 pi, then there is just no comparison triangle. And we cannot write down cut 1 inequality. So only in this case, a comparison triangle on the right exists. Let us consider this comparison triangle. Actually, it is already drawn here. This is a comparison triangle in S2. and this is a comparison triangle for the initial. We have on the right hand side we have triangle y1, y2, y3 in y. We have triangle of such kind in x. It is important that we understand that any comparison triangle in x lies over some comparison triangle here. Any geodesic in x lies over some geodesic in y. So we can always consider those two triangles one over another, and their comparison triangle will be like that. This is a comparison triangle on S2, and taking these segments of lengths R1, R2, and R3, we get this Euclidean comparison triangle. Oh, okay, in 3 space, but it doesn't matter. It is, of course, it is contained in some. Okay, and now we must say that this triangle is thinner than those triangles. So if we take here 2 points, say W1 and W2, well, then distance here on the sphere is greater or equal than this distance. But we can also write down the corresponding points here. This will be y1 as the second coordinate, and on the first coordinate we need to point out some s1, and this s1 is fixed by this property. So it can be uniquely written through all this length of all these segments. Just the formula will be not very nice, but I don't want to write it explicitly. And what I would like to say that these are exactly those 2 points. And now, so it is straightforward that inequality that this segment is shorter than this one is completely equivalent to that this is shorter than this arc. So I hope this is more or less clear. This is a good exercise to do here and do a more precise enumeration of cases. Well, but I forget. Okay, this covers case A. Well, but we still have case B, where there is no comparison triangle on the right at all. Yes. So what happens? What happens in this situation? What happens with the comparison triangle for this guy? Here we have for each pair of x1, x2, we can construct such triangle or such flat triangle with edge lengths R1. This is R2, and this is just distance between x1 and x2. This is distance between x1 and x2, and hence this is phi 1, 2. This is distance between x1 and x2. Well, and an important thing is that this triangle is isometrically embedded into our x. And we have similar two triangles for two other pairs. This is R2, R3, phi 2, 3, and similarly here, R1, R3, and phi 31. But what is important? Now we are in the case when the sum of those three angles is greater than or equal to 2 pi. Yes, so if we glue together these three triangles, then we get not a flat triangle, but we get a triangle on a cone with total angle at apex greater than 2 pi. And what we need to prove that cut zero inequality is always true for such triangle. We have no comparison triangle on the right, so in this situation, this equivalence is just that in this case, cut zero inequality is necessarily true. This is more or less an exercise in Euclidean geometry. Well, the idea is the following, that if we attach those triangles to each other, if we attach them, glue them together, we get a figure like that. Well, and this segment will be smaller than this one. We cannot attach this triangle here, this angle phi 31. This angle is smaller than phi 31. Their sum is greater than pi. So we took here true triangles phi y1, R1, R2, R3, but we have correct angles here, so here we have smaller. So this segment is smaller than those. This R prime is smaller than A. Then what we see? We more or less, if instead of this picture, we consider a comparison triangle for these 3 points in X, what does it mean? Let us introduce some notation. This is A2, A3, and A1. These are lengths of these distances. So this is A2 prime. If instead of here we have exact values A3 and A1, but not incorrect value of A2 prime. This is not a comparison triangle. A comparison triangle has lengths A2, A3, and A1. And in this comparison triangle, the angle of this triangle is smaller than the angle of comparison triangle, since this side is greater than this one, so the angle is greater than this angle. What does it mean? It means that points here are closer to each other than points here. When this is true? This is true until we can come between these 2 points by a direct segment. So if a pair of points is on those two sides and they are closer to here, then they are close enough to here so that the segment goes doesn't go like that, but goes like that. Then the distance here is smaller than the distance here, and the distance in x is even smaller than this one. And in in all other cases, it is the shortest path is through apex, and well, I realize that what I say is not so is not very clear. Let us. I just want to say that all this stuff is about a very simple statement. The statement is as follows. Consider one particular metric space. Just such metric space is cone Euclidean metric with the only singularity cone of total angle greater than 2 pi. Well, this is one particular metric space for each psi. Well, let it be C psi. Just such cone with total angle greater than. So this is a good statement that this particular space is cut zero. So what I'm trying to prove this directly. Actually, it is proved directly, but we need to consider some not very nice amount of cases, but still this is more or less explicit and not so hard. I just don't want to go in details. It is better to formulate this like that. So, since this one is cut zero, these three triangles glue together so that we obtain some subspace of this cone, and this subspace is embedded diametrically to x. So cut zero inequality for in x in this case follows directly from those cut zero inequality. Well, and actually similar reasoning goes in the cases when some of these phi aj are greater than pi. Okay, so we have this very nice, necessary, and sufficient condition. Certainly, this condition is usually used from right to left. Y is usually low dimension, not usually, Y is always low dimension. Its dimension is one smaller than X. So it is, of course, we would prefer to come from smaller dimensions to higher one, and this is a possibility to check the cut zero property starting from cut one property for less dimensional spaces. Actually, this lemma explains why cut one is important for us. Initially, for us, only cut zero is more or less important, since from cut zero we can obtain contractibility of spaces, and we have some good properties. We do not have such good properties for cut one, but cut one is important since it allows us to understand that something is cut zero. But okay, now we have next problem. So assume how to understand that something is cut one. And here a natural idea is to repeat the construction of Euclidean metric cone, but to define a spherical metric cone, similar construction, taken sphere instead of Euclidean. Let us try to do it. There is one problem here, but well, we will face it soon. What? Well, what is the main idea? The main idea is the following. Okay, how we have, let us recall the definition of Euclidean metric cone. What we take? If we take two distances, R1 and R2, and an angle between them, then we just took Euclidean triangle and say, okay, we know how this length, okay, this cosine law, we know this the necessary value for this distance, and this will be the distance. What is an analog in spherical case? In spherical case, again, suppose that we have these two polar distances, R1 and R2, and an angle, but now I would like to live on a unit sphere. And the idea is as follows. Consider a unit sphere and a point on them. This point will be analog of this initial point, origin in plane. Okay, I consider two geodesic, two great circles with angle phi between them. On one of these geodesics, I take distance R1. On the second geodesic, I take distance R2. Then I can compute this distance. Okay, I don't want to write down this formula, but yes, the sphere is of radius 1. The original sphere. Okay, you can easily do some trigonometric and write down this formula. This is a particular function of phi, R1 and R2. Well, so we can try to do the following. So we take some y, and we consider for given geodesic metric space y, we consider such pairs R, y, where R is a real number and y is from y, and we may try to define distance in this way. So if we have 2 points R1, y1 and R2, y2, then again we write down phi as distance between y1 and y2 in y capital, and then we draw such a triangle, and we say that okay, distance between those 2 points x1 and x2 will be this function, which I don't want to write explicitly, but this is a very explicit function. What is bad in this situation? First of all, we have some problem when we go. The first glance is that problem occurs when we go when some r exceeds pi. Well, when then, for instance, the distance between any point pi y and pi y2 will be 0. That's not good. In fact, actually, the problem arises earlier. The problem arises when phi becomes pi over 2. The matter is that I recall that it would be nice to write down this when phi is less than or equal to pi. This is natural analogy with what happened, but we cannot write down this when phi is greater than pi. Well, so in this case, of course, it is natural to write down R1 plus R2. Again, the closest path is through this origin. But that's become bad after this. The matter is that okay, it would be nice that if phi equals pi, we need to have equality. But that's not the case if R1 and R2 are large enough. If we go in opposite directions and go more than pi over 2, then they are closer than R1 plus R2. Okay? If I take just if phi equals pi and I go far enough along great circle, that's not great circle, I'm sorry, along great circle, starting from here, we go far enough. This is R1 and this is R2, and the distance is definitely smaller than R1 plus R2. So that's not good. But everything is good whenever R1 and R2 do not exceed pi over 2. Let us give this definition in this form. So let us consider not an infinite cone. I do not need to consider infinite cone, just some finite cone. Z. I prefer to use Z in this another letter just. Okay, Z is like that. And distance is given by this formula. And then everything that I have said can be transmitted to this case literally. Everything works. And we have analog of lemma 1. I'm sorry for doing this, but still, it is still true. And what is analog of this lemma 2? Analog of this lemma 2 is that in both cases we have cut 1. So this is lemma 3, that Z is cut 1 if and only if Y is cut 1. Well, and this again allows us to go from smaller dimension to higher dimension. Okay? Well, but now an important observation, which is not, this observation is not very clear from such formulations, that these two lemmas allow to proceed by induction on dimension, but they relate local properties with global ones. From the first glance, they are global on both sides. But actually, the matter is that such metric cones is not those objects which usually arise. How to, now I would like to explain how such lemmas can be applied. There is the following very useful source of good metric spaces. they are called PE complexes. PE means piecewise Euclidean. The idea is very easy. Let us consider several convex polytopes with true Euclidean metrics. Just we take some convex polytopes in Euclidean spaces with their induced metrics. Very nice objects. Convex polytopes of different dimensions, maybe, and they can be, there can be finitely many of them or infinitely many of them. That doesn't matter. And now the idea is that we glue these polytopes along isometries of their faces. So we are allowed to glue two polytopes along, but not just topologically along some homeomorphism of their faces, but only along an isometry. So we glue these polytopes along isometries of their faces. And what we get is called a piecewise Euclidean complex. Actually, here some technical difficulties arise. I don't want to go deeply in them. I just want to point out that we need to do something. Well, the matter is, I prefer to give an example. Let us consider a very large polytope. In which those two faces, which are very far from each other, but they are isometric. F1 and F2 are isometric. They just are identical. Let us glue the first one to the second one along this isometry. Okay, the distance between this point and this point, it is very large in the original polytope, but after such gluing, of course, it becomes very small, since this point is identified to this point. I mean that I take points near points which are identified. And okay, so actually, now we need to we obtain such a complex. Now we need to endow it with a metric, and to do this, we actually need to do the following: that we consider for 2 points in X, we consider all possible. I forget an English word. Ломаное, как по-английски. Well, such sequence of segments in Russian, it's ломаное. I forget English word, but we need to consider such paths from one point to another, so that each straight path lies in one particular polytope. And among all such ломаные, we need to take the infimum, the minimum of the distance, and that's a good metric. Actually, here to be honest, we need to impose some conditions. That's definitely true for locally finite complexes, but we need to add some technical conditions on which I don't want to stop. But more or less, this is a rather good object. It is definitely good when the decomposition is locally finite, when these pieces are such that the pieces are not arbitrarily small. So, for instance, there is some epsilon such that all lengths and angles of all polytopes are at least epsilon. So we need some conditions to be to guarantee that an object is not wild. But in good cases, this is actually a good object. And now look. Generally, if we consider a point inside one of the polytopes of largest dimension, then here the metric is just Euclidean, of course cut zero. But when the polytopes meet, we can ask whether this is cut zero or not. This is a natural question. Of course, not always, but sometimes it is cut zero. And similar notion is piecewise spherical complex. PS, it is piecewise spherical. It is standard to mean here that sphere is of radius 1, so of Gaussian-Kovacs 1. All the same, but we take convex polytopes on sphere rather than in Euclidean. So not Euclidean, but spherical convex polytopes. For instance, triangles on spherical triangles, convex and spherical case. Intersections of finitely many hyperplanes through semiplanes through the origin of the sphere. So something bounded by finitely many great hemispheres. Not necessarily. We can always take a subdivision and actually obtain that all simplices are all. In fact, we can always. It is in this case, it is enough to consider simplicial complexes. We can always decompose into simplices, and but it is usually more convenient to consider complexes of rather reasonable polytopes than to decompose them into plenty of parts. And similarly here.
So we can just complement this.
Yes, we can take the complement of the triangle. Usually it is not called convex, since convex is intersection of hemispheres. But actually we can do this. Here the convexity is also not important. We can always consider decompose any polyhedron polytope into convex one. So this is okay. We have this notion, and for such complexes, it is reasonable to ask whether they are cut zero. Well, since in such interior points they are. For such, it is not reasonable to ask whether they cut zero, since, okay, we just take a point inside any polytope and it is not cut zero, even in such very smooth points. But here it is reasonable to ask whether they are cut one. Actually, there is third possible type. We can consider piecewise hyperbolic complexes, the same with polytopes in Lobachevsky space. But for them, a natural question is whether they are cut -1. It is also an interesting case, but it will be not important for us. I just mentioned that it also exists. But okay, how do the complexes piecewise spherical and piecewise Euclidean complexes related to each other? There is a very nice relation. Well, I don't know how to draw complexes of dimension greater than 3, so I need to draw only 3-dimensional. I would like to draw some piecewise Euclidean complex. Well, okay. So, for instance, this is a cube, and we attach here, say, some triangle, well, and maybe some such pyramid, and also triangle. Our polytopes can be of different sides, and so on. And let us consider a vertex. I again forget. I would like to take color chalks, but I again forget to do this. Okay, for each of the cells, this vertex belongs to several cells. For each of the cells, well, say for this cube, we can consider all, when we consider vertex and one particular cell containing it, then we can assume that we are living in some Euclidean space. This cell, the total complex doesn't live in any Euclidean space. It is not embedded anywhere. But any cell separately lives in its own Euclidean space. And in this Euclidean space, we can consider all unit vectors which looks inside this cell. So it is convenient for me. This is only for simplicity of drawing. Let us assume that all these edge lengths are greater than 1. Then these unit vectors are indeed inside, the total vector is inside. But if it doesn't matter, if a cell is small, then still this angle looks inside. That's okay. But it is more convenient to draw when all these angles are inside. Then look, we have unit vector along this edge, unit vector along that edge, and unit vector along those edge. And all unit vectors which go from this vertex inside that cell, they form a spherical triangle, convex spherical triangle on unit sphere. Well, for another, say for this cell, we also have, but here cell is 2-dimensional, so we have spherical, just spherical arc. Okay, formed by such. And here we again have some, generally it is triangle only in this situation. Generally it is some spherical polytope of dimension 1 smaller. And here we also have, in this case, okay, also something. So what we get? If we start from a vertex, then for each cell sigma containing this vertex, we get, let it be L sigma. This is Euclidean polytope. We get this spherical polytope of dimensions 1 smaller than sigma. So this is spherical convex polytope. Dimension is 1 smaller than dimension sigma. And these spherical polytopes are naturally glued together so that we obtain a piecewise spherical complex. This piecewise spherical complex is called the link of the vertex V. The link of V in our piecewise Euclidean complex in X. So if X is the original, and it is denoted by link of V in X. In fact, it is one observation that it is not important that V is a vertex. we can literally repeat the same definition for any point V. And now what we see? Look, locally about V, our complex is a metric cone over this link. It is not globally. It is not true that it is isometric total. But if we take a neighborhood of V in X, a small neighborhood, small enough neighborhood, then it is isometric to a neighborhood of apex in the metric cone, Euclidean metric cone of link V. This is a very important observation. So we have this observation that locally about V, X is isometric to the metric cone over over link of V in X. Then what lemma 2 gives to us? Suppose that all links of vertices are cut 1. Assume that we have managed to check that all vertices of links, all links of vertices are cut 1. Then we cannot guarantee that X is cut 0. No reason for it to be cut 0. The matter is that X is not a metric cone over any link, but it is locally, it is metric cone over link. It follows that cut 0 is cut 0 property for X is satisfied locally. So this is exactly what we called the curvature is less than or equal to 0. So this is corollary of this lemma 2. Corollary of lemma 2 is that if we have this situation, we have a piecewise Euclidean complex. So if X is piecewise Euclidean complex, and for all vertex V, its link is cut 1. Then X has non-positive curvature. Cut 1 is satisfied locally. Once again, we have now we need to consider analog of this for lemma 3. What is analog of this? Suppose that X initially is piecewise spherical, not piecewise. Up to now it was piecewise Euclidean, but now suppose that the initial complex is piecewise spherical. Then the picture is not so nice. The matter is that it is rather unpleasant to draw pictures. The matter is that in spherical case, the tangent space doesn't lie in the cell itself. Yes? So this cell is spherical, and this spherical triangle will lie not in this cell, but in the tangent space. It is not so pleasant to draw it, but the definition is directly the same. We take a vertex and a cell, and in the tangent space to this cell over V, we have those unit vectors which point inside the cell. And they form a convex spherical complex, which is again the link. So the link of vertex is always piecewise spherical. Doesn't matter, we can start from piecewise Euclidean or from piecewise spherical complex. The link of vertex is always piecewise spherical. And in this case, X is locally isometric to this spherical cone over the original complex. And again, this is corollary of lemma 3. Corollary of lemma 3 is that if X is piecewise spherical, and for any vertex V, link is cut 1, then the curvature of X doesn't exceed 1, which means that cut 1 is satisfied locally. So to proceed by induction, if we would like to obtain some, so to check whether some piecewise spherical complex has non-positive curvature, we need to check cut 1 for links of its vertex, for its vertices. If we would like to check local cut 1 for links of its vertices, then we can go further. We can check true cut 1 for links of vertices of links of vertices. And we can proceed in this way, but we always need to go from these corollaries give us only local properties. And we need to find global properties from some source. And, it's not a lot of time. Well, and now I formulate, I would like to formulate two theorems which I will not prove them. They are rather technical, but in fact, there are theorems which allow us to obtain global inequalities from local ones, but with some conditions. I have already formulated one of the theorems. These theorems looks differently in the case of cut 0 and cut 1. These cases are truly different. So theorem 1 is that suppose that X has curvature less than or equal to 0, and we would like to obtain cut 0. And what we need to require is that X is simply connected. And then one can deduce global cut 0 property from local one, but I will not prove this. And theorem 2, if I would like, the same is not true. If we even, I will give an example in a pair of minutes, so that the complex its curvature is less than or equal to 1. It is simply connected, but it is not. It is not cut 0. Well, but the what we need to require is that there are no X has no it's better to say contains no closed geodesics of length less than 2 pi. Then X is cut 1. Well, first of all, an example of a simply connected space, why analogous statement is not true. It is very easy. Let us take a standard S2 of radius 1 with a round metric. Of course, it's cut 1, yes? No problems. But now I make a small hole in it. If I just restrict the metric in S2 to what so X is this S2 with small hole. I would like a space to be compact, so I delete open disk. I remove an open disk. If I just try to restrict the metric, it is not a good metric. The matter, it is not geodesic. There is no geodesic between such 2 points in X. The geodesic goes through hole which we delete. But let us just introduce a new metric. We just say that metric is the shortest path inside X. So we just took initial metric on sphere, but now we say that, okay, here we have a hole, we are not allowed to step there, and shortest path to achieve from one point to another. Look, of course it is locally it is cut 1. The matter is that locally it is a sphere, but globally it is not. Just I take such a small triangle, 3 points on this boundary circle, and of course, well, if this is this circle in another scale, yes, then these are 3 points, yes. What is comparison triangle? This is very small, so comparison triangle on a sphere is almost Euclidean, yes. So this distance in comparison triangle is of course smaller than this one, but distance from here to here is greater than so cut 1 inequality definitely fails. It is not true. But here, well, what is a closed geodesic? Closed geodesic, when usual geodesic is an isometric embedding of a segment, then closed geodesic is an isometric embedding of circle of some radius to X. So, and here we have very small geodesic. Actually, it seems from the first glance that theorems look like very differently, like a completely different condition. In fact, when this theorem is proved, actually this condition, this is for curvature 1. For curvature kappa, the condition would be this over square root of kappa. So for curvature 0, analogous condition is that there are no closed geodesics at all. And actually, here the first step is that if it is simply connected and this is true, then there are no closed geodesics at all. And after that, this is the same theorem. But okay, I'm not going to speak about these theorems. But now we have a break. Well, let us have a break for 15 minutes till 6:15. After the break, we will discuss this theorem together with this lemma, with this corollary, allows us to proceed by induction. So on each, we proceed from smaller dimensional complexes to higher dimensional. So we reduce check for each complex to check for its lengths of vertices. But on each step, we need additionally to check absence of short geodesics. And after the break, we will apply this to Coxeter groups and see how it works. Now let us make a break. Well, let us proceed. So now first I recall what is a Coxeter group. By definition, this is the following group. We take a group generated by some set of generators in all. I will be interested only in the case when the set S is finite. We can consider infinite as well, but in our case, the set of generators will be finite. So this group is generated by finitely many elements, S1, Sn, and the following relations. First of all, each of the generators squared is 1. And second, for each pair of I and j, we have a relation of the following form. Here, Mij is some given symmetric matrix. So Mij equals to Mji, and these entries can be either natural numbers greater than 1 or infinity. We have the following convention that if Mij is infinity, this just means that the absence of the corresponding relation, just no relation for this pair. So what we say? We say that element SI has order at most Mij. Yes? Where Mj is? This is definition. And let us start. I will just say, but not prove, some. There is a standard fact that in fact, if this SISJ has always order exactly Mij. So it could happen a priori that for some matrix we can deduce a stronger relation from all other relations, but this never happens. But this will not be so important for me. This matrix is given, so for each such matrix we have its own group. And today let us start theory of all Coxeter groups is very closely related with such cut-zero spaces, and I will say about it later. But let us start with a very special case. This very special case, but still very interesting one, is called right-angled Coxeter groups. Well, just before coming to right-angle Coxeter groups, let us note two remarks. First of all, actually, this is matrix without diagonal. Their diagonal entries have no sense. Yes, these are only for I equals to j. So symmetric matrix without diagonal.
Can't we think of them as ones?
Yes, we can, but just it is not important. But there is one very special case. Let us consider matrix with 3 below and above the diagonal and 2 everywhere else. And this leads us to symmetric group. if we have n generators, then this is Sn plus 1. With its standard presentation by consecutive transposition. So we have plenty of nice examples starting from such interesting groups. Okay, but this is in a sense opposite example. Opposite example, rectangle means the following, that all Mij are either 2 or infinity. No intermediate values. Only 2 and infinity are allowed. What does it mean? What is the case Mij equal to? Mij equal to means that Si Sj squared is 1, but Si and Sj are elements of order 2. Hence, this is equivalent to Si Sj equals Sj Si. So Mij equals 2, this is exactly that the corresponding two generators compute. So right angle Coxer group is just the following. We have some amount of generators, each of them squared is 1, and some pairs compute, and some are not. This Coxeter group, it is natural to describe such Coxeter group by a graph. We just connect those 2 points which commute. If they commute, we connect. So edge means commute, and absence of edge means no relation. We have only this situation. So starting from any graph on n vertices, we may produce a right-angled Coxeter groups. Generators connected by an edge commute. Generators not connected by an edge not commute. Well, now, well, no. Graph, a simple graph without multiple edges and loops. We just need to specify which pairs commute and which are not. This is just graph. Well, it turns out that, well, our goal is, during last lecture, then after last lecture, I remember that I several times make a not very correct statements. I said that I'm going to construct classifying space for Coxeter group. There is one natural reason why it is not so easy to construct a classifying space for a Coxeter group. Let us forget for a moment from all this stuff. And, well, there is one general statement. Suppose that a group contains an element of finite order. Then the classifying space cannot be finite dimensional. It is a very simple observation. The matter is that if some group containing an element of finite order acts freely, if a classifying space is finite dimensional, then this corresponding, so space BG is finite dimensional, its universal cover EG is also finite dimensional. Group acts freely, but then subgroup generated by this element, which is just some finite cyclic group, also acts freely on EG. And then we would obtain that EG quotient by this action is the classifying space for this cyclic group. But we have computed the homology of the cyclic group, and we saw that it has cohomology and homology of arbitrarily large dimension. So it is completely impossible to have a finite dimensional classifying space for any group which has at least one torsion element. So actually what I'm going to construct a nice finite dimensional cell complex on which Coxeter group acts with finite stabilizers. It is not free. The action is not free. It cannot be free on a finite dimensional complex, but it is the best we can achieve. And this means that we will understand classifying spaces for all finite index subgroups of Coxeter groups. Not of Coxeter group itself, but for finite index subgroups. This is still a very good situation. We still, for instance, with rational coefficient, we immediately understand whole homology of Coxeter group itself, since passing to a subgroup of finite index doesn't change a rational homology. But a more precise formulation is like that. And my goal now is to construct cut zero space on which first we start with the right angle Coxeter group acts by isometries and with finite stabilizers of points. Well, we start with the following. The construction is as follows. Well, I would like to construct the complex. It will be denoted by sigma. First, the complex will be cubical, so all cells will be cubes. And they will be very standard cubes, just standard Euclidean cubes with standard metric. So nothing difficult, just standard and dimensional cubes. And the idea is as follows. For the set of vertices, we take the group itself. So vertices are just elements of the group. So that W is the set of vertices. Now, the cells look like in the following way. Consider an arbitrary clique in this graph. What is clique? Clique is a complete subgraph. Subgraph such that some subset of vertices such that all vertices are pairwise joined by edges. So suppose that we have some clique. Well, for instance, this is clique consisting of 5 vertices. Let their numbers be I1, I2, Ik. Then we can consider then the corresponding generators pairwise commute. The corresponding generators Si1, Sik pairwise commute. And so we know very well which subgroup they generate in W. Of course, if we have k elements of order k, of order 2, which pairwise commute, then they generate subgroup isomorphic to direct sum. I prefer to speak in multiplicative form, so they generate a subgroup generated by isomorphic to k, to the direct product of k examples, k copies of the group of cyclic group of order 2. They generate such a good question is why this group is not smaller. Okay, they have order 2, they pairwise commute, but maybe we have some degeneration. But this doesn't happen. The matter is that starting from any right-angled Coxeter group, we can add additional relations of such form for all other pairs. So we have such relations for some pairs. Let us add all other such relations. And what we get is exactly, then of course we get just C2 to the power n. Yes? The Coxeter group corresponding to complete graph. So this group can be smaller than in this case. After some quotient, it is C to the power k, so it is okay. Well, and now let us take an arbitrary element W, and starting from this element, it is better to draw an example. I prefer to draw an example for k equals 3. I consider a cube. This is W. Along the first coordinate, I add SI1 from the right. From the second coordinate, I add SI2 from the right. Here I add, not add, but multiply by SI3. These are 3 coordinates. Here I have SI1 and SI2, and the order is doesn't matter since they commute. And here I have SI1, SI3. Here I have WS I2 SI3, and here is WS I1, SI2, SI3. So these elements can be naturally organized as vertices of unit cube. And of course, in an arbitrary dimension, we do the same thing. Now, so what is this set of group elements? This is a left coset W by this group. Let it be just C2 to the power k. This is the left coset by the group generated by this SA. So for each such coset, we have the corresponding cell. Note that we could take, instead of this W, we could take for W, say this one, for W prime. Well, but still the cell is the same. So the number of cells is number we need to specify is as the number of cosets, we have no a particular cell for each W. We take a cell for each coset. If 2 elements lie in the same coset, then the corresponding cells just coincide. So we have as many cells as cosets. And look, any face of this cell is exactly the same cell for smaller clique. So if this, for instance, this below cell, this cell, horizontal cell, is a cell corresponding to clique I1, I2, and so on. Now let us just glue all these cells together, just along natural well, they are already glued together. We just, if two cells have identical phase, then we glue them along this phase. This is exactly sigma. And now the metric is that we endow each cube with standard Euclidean metric of cube with edge 1. And we glue these cubes together, and as usual in piecewise Euclidean complexes, we say that distance between 2 points is just the smallest, I again forget this word, smallest length of such paths consistent of segments, each one a line in its separate cube. Well, this is the construction. The construction is over. Now the group W, of course, acts on this sigma just by left multiplication. If we multiply from the left, then our structure of, we are not allowed to multiply from the right anymore. This will broken our structure. But we can multiply from left, so it acts by left multiplication. And a nice theorem is that this sigma is cut 0. Hence, in particular, it is constructible. Actually, to be honest, there are plenty of ways to prove that it is constructible without proving that it is cut 0. My viewpoint is that this context is the most conceptual, is the most ideologically, it is the best way to understand this from cut 0 property. So theorem, well, as far as I understand, this theorem is due to Michael Davis. I am slightly not sure that it is completely true. Maybe in right-angled case it will be earlier. In general case, it seems that it is definitely theorem by Davis. But as for the proof, this is not by Davis. Sorry. Contractibility is by Davis, but cut 0 was later. Well, actually I did not look through the history who is the author, so so the theorem is that this sigma is cut 0. Well, the key lemma, I'm I cannot say exactly who is the author of about the authorship of this theorem, but the key lemma is here is known to be Gromov's lemma, and maybe the theorem is also in this formulation is also his. But the construction of is earlier. Gromov's lemma says again. Gromov's lemma is a lemma which will allow us to use this corollary and to understand that curvature is less than or equal to 0. So this is a lemma about links of vertices. But before formulating it, let us look in more details on a link of a vertex. First of all, links of all vertices are identical. This W acts by isometries, and it acts transitively on vertices. We can always act. So what we are interested in, we are interested only in link of vertex 1 in sigma. 1 means, an element of the group, the unity of the group. So let us forget about this W and just I would like to consider a cell containing 1. Okay, but then look, then these one-dimensional faces connecting 1 corresponds to generators, to sum of generators. And these are exactly vertices of the corresponding simplicial complex. First of all, link will be simplicial complex. The matter is that for each cube, the corresponding cell of link is a simplex. And it is not a simplex. It is a simplex with very standard metric. It is so-called right-angled simplex. Simplex, spherical simplex with all dihedral angles right. So in two-dimensional case, this is just standard simplex which is obtained as a standard triangle with 3 right angles, which is 1/8 part of the sphere. Okay, so our complex will be glued out of such simplices. Moreover, we can easily say what is the combinatorics of this complex. Look, vertices of this complex are in one-to-one correspondence with generators, not with group elements. Group elements is some set which exists but is not very efficient. We cannot work efficiently with group elements. It is not so easy. But generators is something very explicit. So for this link, so if we take this if we take this L, this is link of 1 at sigma, then first L is right-angled piecewise spherical complex. I mean that each cell is a right-angled simplex. Right-angled piecewise spherical simplicial complex. And second, we can easily describe its combinatorics. So vertices of L is exactly S. To be more precise, okay, it is convenient to assume that vertices are no. Vertices is just all S. But simplices, well, simplices are spanned by cliques of this gamma. Exactly. By complete subgraphs of gamma. And that's the complete. So combinatorics is immediately obtained from graph. And this L is called the nerve of this Coxeter group. And what is Gromov's lemma? Okay, there are two formulations. and we will easily see how one follows from another. So one formulation is that actually Gromov's lemma is about these right-angled PS simplicial complexes. So Gromov's lemma says that a right-angled PS simplicial complex is cut 1. This is exactly what we are going to check. If and only if it is a Flagg complex. Flagg complex is if and only if it is a Flagg complex. What is a Flagg complex? Flagg complex is the following purely combinatorial property, that there are no empty simplices. If some set of vertices are pairwise joined by edges, then we have the corresponding simplex in our complex. So this is just a definition. Definition. A simplicial complex is Flagg if any set of vertices is a simplex whenever vertices in sigma are pairwise joined by edges. So it is not allowed, for instance, that 3 vertices are pairwise joined, but there is no triangle in our complex. If there is such situation, then it is not Flagg. Flagg complex, whenever we have 3 edges, we have a triangle. Whenever we have complete graph on 4 vertices, we have a tetrahedron. If this condition is satisfied, then it is Flagg. Actually, though it is true in both directions, I am interested only in this but if. We are interested that if it is a Flagg complex, then it is cut 1. Why? The matter is that the nerve of a Coxeter group necessarily is a Flagg complex. We just take a graph and span a simplex by any click. This is always Flagg complex. If vertices are pairwise joined by edges, then we have all these edges in graph, then we span a simplex by click. So in fact this is true in both directions. Flagg complexes are exactly those which are obtained from graphs in this way. So nerve of Coxeter group is always a Flagg complex. And it turns out that this is exactly a necessary and sufficient condition for a right-angled PS simplicial complex to be cut 1. It is not so easy. It is just only one strange case where it turns out to be rather easy to give such necessary and sufficient condition. If we consider not right-angled, but some arbitrary, there is no similar to this. But in right-angled case, it turns out that it is this lemma is true, and it is not very hard. We will prove it just now. But before doing this, let us understand that this lemma implies the theorem? Well, it almost implies the theorem. We see that, okay, by lemma, the nerve is cut 1. So by this corollary, we obtain that our sigma has curvature less than or equal to 0. So the only thing we need to understand is that this sigma is simply connected. Well, now how to understand this? Well, why proposition that sigma is simply connected? Actually, this part is made by hands. Let us take what is a loop in sigma. Any loop can be approximated by a loop going along edges. This is usual theorem of cellular approximation. So let us take for of course our complex is connected. Let us take 1 for base point and consider any loop. So we start from 1, then we go by along some edges, we travel along this sigma, and we arrive to 1 back. But what is the traveling along edge? Look, any edge connects some, this is just one of generators, and any edge connects if we have some W here, then here we have W multiplied from the right by certain SG. So we have such path. We always multiply from the right by certain SG. Let us just go along this path and enumerate and consider which SG are in this path. So we have SI1 on the first step, SI2 on the second, so that here is SI1, SI2, yes? SI3 on the third step, SI4, and so up to some SIN. What? Then we know that we return back to 1. So we have the following equality in our group. SI1, SI2, SI3, etc. SIN equals 1. This is just the equation that we return back to 1. But now we know that by definition of Coxeter group, all relations in the Coxeter group follow from relations of such form. What does it mean? This means that this word can be reduced to empty word by the following moves of 3 types. One move is that we can commute, but only if they commute, only if ij is in an edge of gamma. Second, we can, if si goes twice, then we can replace it by empty set or vice versa. Well, 3 types, since this is in both directions, so that's all. We have no other relations, so any word which is 1 can be reduced to empty word by such operations. But okay, these operations correspond to homotopies of this path. The second one corresponds to the following, that okay, if we have such path, then we can modify it in the following way, that we go up to here, then go along some edge, return back, and then proceed. This is trivially homotopy. But if we have here omega Si and here W as Si as J, then we can swap this along two-dimensional phase. And this is another move. So for each move is just homotopy across some two-dimensional phase. And performing these homotopies, we obtain homotopy from this this loop to the trivial one. So hence it's simply connected. Any loop is. But the importance of this cut zero of all this cut zero theory is that from simply connectedness is proved just by hands without any theory. But simply connectedness implies contractibility. Yes. So of course the most important. I forget to write it down. That hence the most important corollary is that hence it's contractible. Well, now let us prove Gromov's lemma. Now we may forget about Coxeter groups. It's just about arbitrary flat complexes. Well, I will mostly prove it in direction if. Vice versa, it is more or less. Vice versa, I will not be so precise because it is not so important for us. But it is true in both directions. Okay, let us try to prove this. So I want to prove that such a simplicial complex is flat, or is cut one. So I want to prove two things. Let suppose that L is a flag right-angled PS simplicial complex. We need to prove two things. First, we need to prove that its curvature is less than or equal to 1. And second, we need to prove that there are no short geodesics. There are no geodesics of length smaller than 2 pi. This is our theorem from local to global, which I haven't proved, but still it is the crucial tool here. Second, we need to prove that L contains no geodesics, closed geodesics of length smaller than 2 pi. Let us start with the first one. The first one, we know that it is a PS simplicial complex. So to understand that its curvature is less than or equal to 1, we need to proceed by induction. And we need to look on its links of vertices. But okay, if you have a flag complex, then I claim that the link of each vertex is again flag. Well, simplices in a link correspond to simplices of one dimension higher of the initial complex. If there were an empty simplex in link, there would be a one dimension higher empty simplex in the initial complex. So first observation is that link of a vertex is again flag. And second observation is that it is again right angle. The matter is that, well, let us draw it here. If we consider a right-angled spherical simplex, well, just it is some, we can think of this as intersection of unit sphere with some positive orthont in Rn. Let us draw it like that. We have in Rn a positive orthont, and here we have this looking on us this right-angled simplex. Then the link of a vertex is it lies in the tangent plane, and it is exactly intersection of this tangent plane with positive orthont of one dimension smaller. So we again have a right-angled simplicial complex. So link of vertex is right-angled. And these two properties say that we have cut one property just by induction. So this follows from the same Gromov lemma by induction. And this is the only thing we need to check. This does not follow by induction. This must be checked by hands, more or less. So this is exactly what we actually need to prove. We need to prove that if we have a flag right-angled PS simplicial complex, then there is no closed geodesic which is sufficiently short. How one can prove theorems like that? There is the following very nice and short argument. For we have such complex. Well, and we assume that we have a closed geodesic. Well, so something like that. For each vertex V, let us consider an open star of this vertex. This means that we take the union of all open simplices that contain this V. Well, closed star, let us draw it as closed star is just the union of all simplices that contain V, and I would like to delete the boundary, to delete those simplices which do not contain V. So this is an open star. I will denote it by ST with this 0 of V. This is an open star. And I would like to consider all vertices V such that our geodesic, our closed geodesic, intersects an open star. Of course, we are not interested in those vertices which do not intersect, such that geodesic do not intersect their open stars. Let us just consider all vertices. Let V1, Vn be all vertices with the following property, that gamma intersects open stars of these VIs, so these intersections are not empty. Okay. Now there are two cases. First case, it may happen that these vertices altogether span a simplex in our L. In the second case, that they do not span a simplex. So consider first this very trivial case, that these vertices span a simplex. Then I claim that our geodesic always is contained in this simplex. Well, look, I write down the case of n equals 3 just. Okay, we have these vertices. Assume that our geodesic at least once goes out of this simplex. Then it gets somewhere when there is at least one other vertex. So these are not all vertices which contain our geodesics intersect an open star of this W. So this may not happen. If it goes out, then these are not all vertices.
And here we use it in Slack.
Well?
And here we use it in Slack.
No, here not.
This full syntax is double is a syntax.
No. I say that just that if there is such W, then this is not correct set of vertex. We take all vertices. The flag will be later. Here we use nothing. But then, well, it's a trivial observation that if we have a round sphere of radius 1 and we have its intersection with positive orthon, such right-angled simplex, well, there is no closed geodesics inside it. In such convex simplex, there are no closed geodesics at all. So in this case, no closed geodesics. So this case is impossible. Case second, that it is not a simplex. And now, not a simplex. And it is now that I want to use flagness. Since it's flag, this means that there are two vertices which are not joined by an edge. Among those, V1, Vn, there are vertices which are not joined by an edge. So in this set, without loss of generality, we may assume that these are V1 and V2. Just a number in these vertices. We may assume that V1, V2 is not an edge. But then a rather easy observation that if two vertices are not joined by an edge, then their open stars do not intersect. Closed star may intersect, but open star may not. If there is a point in open stars of both, then it is contained in simplex which has both these vertices. So they are disjoint. And now my goal is to prove that the intersection of gamma with each of these stars has length at least pi. then the length of gamma in total is at least 2 pi. So now, starting from this moment, I would like to consider the intersection of gamma with, I denote it just by V, with an open star. We assume that it is non-empty. I claim that if such an intersection is non-empty, then its length is at least pi. Well, how to prove this? Well, I would like to make a drawing which is at least three-dimensional to avoid some triviality. So, okay. This is one right-angled simplex. This is the second one. Okay, something like that. And we have piece of geodesic which starts on some point, this is V. It starts on some point of the boundary of star. It goes inside the star. This is our condition. We know that it at least once it gets into the open star. It goes somewhere inside, and it arrives to the boundary of the star once more. And we know that it is, at least locally, is a geodesic. Closed geodesic is not any its piece is a geodesic. The matter is that closed geodesic, only its pieces which are less than half are geodesics. Otherwise, it is not short as geodesic. But small pieces of closed geodesic are geodesic. So we know that this gamma is locally geodesic, at least. Okay, what can we say? We can say that let us we can go along gamma using some natural parameter. We just introduce a parameter which is, let S be this parameter. And for each moment, we may measure the distance, this such straight distance to V. Yes. This is another parameter, R. Now let us assume that the length of, gamma intersect with this star of V is less than pi. Well, let us, we have union of such segments from V to points of our. Let us develop this union of segments onto round sphere in the following way. So I take round sphere, I take here some point, which is, okay, we can say that it is comparison point for V. And let us just for S, I take the longitude. So assume that this is North Pole, and I have longitude. So S develops from 0 to something which is less than P, to some L which is less than P. this is 0, and it develops to, so the S grows in this way up to some L. S is just longitude, just such angle. And now in each section, for each S, I have here some R of S, as given here. So I have this R of S and it is always in between. And at least once it is strictly in between. And so we obtain some path like that. Okay. I claim that this must be also locally geodesic. The matter is that assume that this one is not locally geodesic, so we can replace some short path by another path, which is shorter. But then we can do it here inside the surface formed by all these segments. This surface is just isometric to this one. At least locally isometric. We locally have the same surface. If it was not shortest here, it was not it would not be shortest here too.
It will be not here when our point is on edge of our triangle.
It doesn't matter. If we can meet here some edges, faces, but we just take this. I do not claim that it is isometric totally, but locally it is isometric. Well, actually we need only in one direction, and in one direction it is very simple. I need only that distances here are not greater than distances there. Да.
Вот мы взяли два куска.
Да.
Это сферический треугольник склеили. Вот правда, что вот окрестность точки на склейке, она просто такая же, как окрестность точки на сфере.
Это не окрестности. Вот в этой поверхности, да. Здесь вообще очень многомерная штука, но в ней мы вырезаем только те, которые над кривой. Тогда да. Здесь мы идем через некоторые очень многомерные симплексы. Но мы идем вот в этой кривой и берем объединение отрезков, которые идут в точке этой кривой. И это двумерная штука. И она вот так ложится на сферу. Well, and now if the distance is less than pi, then there is no such geodesics, of course. This is just easy property of a sphere that the geodesic goes just along the boundary. If the distance is smaller than pi on the equator, then there is no local geodesic like that. So that's all. Well, this is one direction. This is direction if. I just, in few words, I just say what is the main idea in the case of if we would like to go opposite direction. In fact, okay, not flag complex means it contains an empty simplex. Yes? Assume that complex contains right-angled complex contains an empty triangle. So we have three edges so that this is not a triangle. Then this is a closed geodesic of length 3 pi over 2. Length of each edge is pi over 2. So the total length is 3 pi over 2. And it can be checked, it's a good exercise, that if we have no this simplex in flag complex, or in simplicial complex, if it is not flag and we do not have this simplex, then this is actually a geodesic. We cannot decrease its. If there was such simplex, then it is not a geodesic. We can decrease its length. But if this is not a simplex, then this one is geodesic. So we see a closed geodesic of length less than 2 pi. So it is definitely not cat1. In cat1, we cannot have closed geodesics. Indeed, if we have a closed geodesic of length less than 2 pi, then we can take here two opposite points and one other, and to consider a comparison triangle. Just it is even better. Well, we may take slightly. This is slightly smaller than that one. We can consider such a comparison triangle, and a comparison triangle will be almost flat, or almost degenerate. It would be completely degenerate if we get the antipodal point, but here it will be almost degenerate. But it's actually it's better to say to take antipodal points than it's truly degenerate. It's better to proceed as so the comparison triangle is degenerate, but these 2 points, this and symmetric one, are very far away from each other, but in comparison triangle they just coincide. So cat1 inequality definitely fails. But then, okay, if a complex which is not flag contains an empty triangle, then it is not cat1. But if it contains an empty simplex, then we need to take link of a vertex of one of vertices in this simplex of next, and so on, until we get an empty triangle. So in some link, we will have an empty triangle. Then it is not cat1, and then by induction, it is not cat1. All of them are not cat1 by such lemma. Okay. So this is just idea, and I don't want to be precise here. And well, what is the summary? The summary is that for an arbitrary right-angled Coxeter group, we constructed very explicitly as very good cell complex, very nice cell complex. It is easy to work with them. It is just cubical complex with very nice metric, which is cat0, which is contractible. So, yes, I haven't said this. We have very few time, but it is actually a trivial exercise that W acts on this sigma with finite stabilizers. It is completely obvious that it is true, and so it is not, as I said, it is not the construction of a classifying space for the Coxeter group itself, but for any torsion-free subgroup, we just take quotient of this sigma by a torsion-free subgroup, and we obtain a classifying space. And such constructions can be used to compute homology with these groups, for instance, to understand something about them, so and so on. And in particular, and also the last promise for the next lecture. During the next lecture, I will say what is the correct analog of this construction for an arbitrary Coxeter group. Up to now we considered only right-angled. The situation is completely parallel. The only difference is that the analog of this statement, which is here rather short, will be rather complicated, and I will not give it proof, but just it has some work, several cases, and so on. But all the other is. But it is okay. This will be next time, and then we will use all this to understand something about homology of Coxeter groups and their subgroups. And well, the last one that we have 2 more lectures next Friday and 16th of December. Well, so okay, that's all.